Hello and welcome to this tutorial on how to make atom probe samples using a focused ion beam. I'm Peter Felfer and I'm from the Australian Centre for Microscopy and Microanalysis at the University of Sydney. We have a strong focus on atom probe tomography here, and I myself have been specialising in making atom probe samples using a focused ion beam, which includes a whole variety of projects. And I was, for a recent workshop, I was asked to give a comprehensive overview on how to actually do that, with a focus on things that you wouldn't be able to find in a publication, like settings on microscopes, how to move stages around, just a basic rundown, just to give an introduction for someone that's just starting out to do that. And so I thought I'll do that as a video tutorial because the whole process itself is very visual, and I think it's most helpful for people if you actually just show them, okay, take your sample, do this, do this, do that, mill this way, mill that way. And the first thing that I'm going to start with is plan lift out. So there's going to be 3 tutorials on lift out, one on plan lift out, one on cross-sectional lift out, and one on double cross-sectional lift out. And I'll go into detail of what the different things actually mean. So what do we mean by plan lift out and cross-sectional lift out and double cross-sectional lift out? Is essentially how the final piece is oriented with respect to your original sample that you had. So the first and the most simple one that I'm gonna give you a rundown on is the plan lift out, or what we call plan lift out. Just imagine if you've got a thin film on a substrate, your thin film would be sitting flat on your support structure. If you've got a grain boundary, the grain boundary would be sitting upright in your lift out piece. And it would also be what you would do if you do bulk lift out, simply because it's the easiest thing to do. By bulk lift out, I mean if you have anything that in the world of atom probe lift out is bulk, so anything that any feature where the dimensions are more than a couple of microns in any direction, so that your entire lift out piece just consists of your region of interest. As an example for a plan lift out of a thin film, I've got some quantum dots here. So these are quantum dots that we've got in a collaboration with Lan Fu from the Australian National University. And if you would pull them out just with plan lift out, you'll turn them into a sample like the next slide, what you're seeing here. And finally, you will have the region of interest in the atom probe sample, so that the layers are perpendicular to your measurement direction. As a support structure, we're using molybdenum TM grids. So the grids that we're using are SPI 100 mesh molybdenum grids, simply because they have a 30 by 40 micron cross-section, which means they have a cross-section that's almost a square, which gives you relatively round pins when you electropolish them. And we've got our special holders that you can see here, which allow us to move the specimens later between the focused ion beam system and the transmission electron microscope and the atom probe without any problems. And also we can put the support structure in a variety of different ways, which will come in handy for some of the other lift out things that we're going to be doing. If you want to use these holders yourself, you're welcome to make some of them. The design is published in the publication you'll find at the end of this video, or you can try to get some of us. The holders, actually, if you want to do TM on them, they only fit into JO TMs, they don't fit into FEI TMs. FEI TMs generally have very slim holders, so it's a little bit difficult to make any attachments to them. The basic assembly for the lift out is shown here. So that's my little stage that I've got for lift out. And with the blue arrow, you've got the you've got the sample marked, and with the pink arrow, you've got the holder marked. And so basically the holder is standing upright, the sample is lying flat, and that's the basis for our lift out. Cairney, the company that makes the nanoprobes, also sells support structures. They're made of silicon with a reactive ion etching process. And for this sort of lift out, they're also suitable. For the other sorts of lift outs, they're not suitable. But for this one, there's no reason why you wouldn't use them. So whichever one you prefer. If you need to do TM, you need a grid holder. If you don't need to do TM, you might be happy with the chemical support structures. So our holders that I've used for this tutorial, as I said, they also fit into gel TMs, because the gel TMs, they've got these dummy holders which have a little clip at the end. They just clip in there, you put them into the TM, off you go imaging. So there's you've only got single tilt, but that's usually enough to just have a look or use the image to calibrate your reconstruction, and you're relatively quick in and out. Alright, so let's go to the lift out assembly now. The lift out assembly is you've got your film lying flat and your holder upright, just like you saw in the photographs before. And while I'm walking you through this tutorial, on the top left you'll be seeing what you would be seeing in the ion beam view, and on the bottom left you'll see what you would be seeing in the electron beam view. On the right, in the middle, you see what you would see in the chamber scope in the size instruments. In the FEI instruments, it looks a little bit different. And on the right side, you've got a little bit of an overview. All right, first thing you need to do is you need to tilt the stage towards the ion beam so that the surface of your thin film is perpendicular to your ion beam. This is a stage tilt of 52 degrees on the FEI instruments and 54 degrees on the size instruments. And this will then allow us to get going with the first cuts. So the first cuts mean that we cut the basic shape of the bar. In this case, we want to do 5 lift out pieces, and maybe also produce a small TM sample as a reference from the remaining bar. Before you do that, you might want to put down some protective capping, depending on whether you've got a thin film or bulk sample or just a grain boundary. So there's actually a variety of choices. The easiest one is just putting down something in the FIB, but you can also put down or deposit some sort of film, some sort of sputtered film beforehand. As long as you entirely remove the film that you've put down, it doesn't actually matter very much. The only thing about it is that you want it to be as fine crystalline or even amorphous as possible, simply because then you get less milling effects from the crystallinity of your deposit. So there's a variety of choices out there. There seems to be an agreement that sputtered deposited nickel gives pretty good results. In my opinion, platinum is okay. So platinum, trimethyl platinum, whatever is in a gas injection system in your FIB is a pretty good choice if you fully remove it. If you can't fully remove it because you need to have a look at the very surface, you have a variety of choices, of course, of ex situ methods. In our Auriga system, we have a very helpful way of doing this available, which is using carbon deposition, using naphthalene. And the carbon that you deposit is actually fully amorphous, and it's got a very low sputter yield, which is very handy. The problem, of course, is if you have a carbon cap on your sample, the likelihood that it's actually gonna fail in the atom probe is very high. But using the electron beam and water vapor, if you've got water vapor available, or in the FEI system it's called selective carbon etch, you can actually fully remove the carbon that you've deposited, and that's a very very handy method of producing high quality samples from relatively difficult samples. I'll go more into detail about the fine milling, deposition, all of these things, and especially the welds in some other tutorial. But bear in mind that's a very important choice that you take very early during the preparation of your samples. Once you've done that, you're good to go with the milling. So the milling, about it yields 5 samples, which is pretty standard. It's usually about 20 microns long, and the cutouts are about 5 microns wide. Don't try to go too narrow in the beginning to save some time. Just general comment on fibbing: if you think something's going to save you 5 minutes, it's probably going to cost you an hour in the end. So don't try to go too tight with the dimensions. You don't need to put a deposit down. If you do that, that's the entire length of the bar, because in the end, on one side you're going to attach the micro manipulator, and on the other side you're going to cut the bar free. So this just takes a little bit of the time away, or shortens the time that you need to deposit the protective cap. The coarse cutouts can usually be done at about 5 to 7 nanoamps on the FEI machines. The also physics guns on the size machines that have very nicely optimized high current spots. So I've gotten bars, very nice bars, up to 16 nanoamps. If you're at 16 nanoamps, for example, a bar cutout takes about 2 minutes. So pretty much the highest current where you can get relatively decent cutting. On most of the FEI machines, it's advisable at the end to do a little bit of a fine cleanup cut at 1 nanoamp to get the final geometry. And sometimes I find it necessary on the size machines as well. In terms of depth of the milling, so I usually go by time rather than depth. In the end, you want it to be about at least 4 to 5 microns deep, so that you have enough space to not reattach your sample with the other milling steps. So from redeposition, you can actually reattach your samples. Usually this means that on most of the metals, this will take about 15 to 20 minutes to mill. On things that mill faster, like silicon or gallium arsenide, it might only take 10 minutes to mill. If you've got something with a very low sputter yield, it might take a little bit longer to mill everything, but about 15 to 20 minutes is a good time. Once you finish those cuts, you need to tilt to a lower angle. So usually I want my bars to have an angle of about 30 to 45 degrees, depends on how tall I wanted to have it in the end. So you just minus that from the 52 or 54 degrees the stage is at, and then you'll know what tilt you need to go to. Next step is fairly easy. You just do a cut that takes the bar that you've milled from above and cuts the backside of it so that it's freestanding underneath. Whether you cut the lift outside first or later, that's actually optional. You can just do that. You can do that also just before you lift your bar out. You usually can see pretty easily whether you milled through or not if you've got enough space on the other side, because you'll get this glow on your iron beam, simply because as soon as you've cut through, you will get secondary electrons resurfacing on the other side, and it will produce a little bit of a glow and shows you nicely whether you've cut through or not. Once your bar is actually freestanding on the backside, you just tilt back to 0 degrees of your stage tilt, so that the sample is perpendicular to the electron beam, and that's where the first fiddly part actually starts. So the actual lift down part. So what you need for that is you need to then insert your gas injection needle or microstage if you're in a size system, and your micro manipulator needle. And the way you usually do that is you actually drop the stage down, and then you move in the gas injection system and you move in the micro manipulator needle. And then you move the stage to the micro manipulator needle, which is sitting at the coincidence point and not the needle to the not the needle to the stage. So stage to the needle, not needle to the stage. That's a good practice. And the very last step that you do actually is you move your micromanipulator needle a little bit back, just a tiny bit, and drop your stage, and then move the needle to the stage if you can. The reason for that is that later, when you do the lift out, you just want to be able to drop the stage under the micromanipulator needle, and that's a little bit difficult if your stage's got a little bit of backlash and the last move you made was up, and then you're trying to move the stage down. You'll get a little bit of sideways shift because the stage got backlash, and that can break the lift out bar of the micromanipulator needle or just crash it into something. So the last stage move you want to make before you attach the needle to your lift out piece is actually down. The whole assembly should then look something like what you can see here on the image. So the lift out piece is attached to the micromanipulator needle with a little platinum deposit in this case. What sort of deposit or deposition conditions doesn't matter very much. This weld doesn't need to endure very high stresses or anything. So just make sure that you've got a decent weld, that it's not gonna fall apart when you're trying to move it around or anything. And then if you've done everything right, you just drop the stage underneath your lift out piece, and you should have it. You should have it on a micromanipulator needle, just like you see it on the image here. Also, if you're in the FIB systems, maybe lock the stage, because you might accidentally click somewhere on your screen and the stage just might move, and while you have the lift out assembly like this with the needle attached to the chamber and your sample attached to the stage, if it accidentally moves, everything breaks and all your efforts up to here were for nothing. Once your lift out piece is on your needle, then you just drop the stage, as I said before, and you move the stage over to where your holder or where your support structure is. In our case, it's the TM grid holder, and you just move your sample over one of the pins. You can see that in electron beam view, right where your pin is, and then you move the stage up until it touches the lift out bar. The last little bit is a little bit finicky, so try to be careful when you're aligning the whole assembly and moving the stage up. The last 1 or 2 microns on the mechanical FEI stages, I like to do by hand, just because you can, and it gives you pretty good control. On the Helios systems, because they have got a very, very good stage, I tend to just literally ram the support structure into the lift out bar. It will stop immediately and it will be perfectly aligned. So that works very well. On the size instruments, there's a little bit of backlash sometimes on the stages, so you move everything as close as you can. It's a pretty good mechanical stage. So you move everything as close as you can, and then maybe move the micromanipulator down the last say half a micron or something, and then the 2 pieces should be touching. Usually the micromanipulator and the stage are not perfectly connected in terms of electrical conductivity, and that can come in handy at that point, because you will see the in the ion beam view, especially, you will see the color or the brightness of the lift out piece change as soon as it touches. So as soon as it gets an electrical contact, and then you've touched and you've got good alignment there, and you can start filling up the gap and attaching a lift out piece to support structure. So with the support structures, there's one thing that I always tend to do before I do the actual lift out, which is cutting the support structure. So if you have the micro tip arrays, you don't actually need to do that, but I still do it because it gives you a fresh surface. If you use the grids, you need to do it anyway. So all you need to do in this case is while your support structure is sitting flat, so the pins are parallel to your electron beam axis, you just cut off the top bit so that the top is about 1 micron to 1.5 microns in diameter. Of course, if you use the posterior is already 2 microns across, it's unfortunately a little bit on the large side. What this does is, well, first it gives you a fresh surface which doesn't have any contamination on it, apart from the obvious gallium contamination. And the other thing it does is it gives you a geometry that looks something like, in the ion beam it looks something like what you see here, which means that in the ion beam that you're using to deposit in this stage, you can actually see that both facets that you're depositing on are looking towards you. And that is very important. So if you do electron or ion beam assisted deposition for structural welds, or for any kind of weld really, geometry is everything. So having the right deposition geometry will make a difference on whether your weld is going to last or not. Deposition conditions also have an influence, have a great influence, but the most basic thing you need to get right is getting the right geometry. And from the ion beam view, while you're doing the lift out, this is as good as it gets, because you are forced into the geometry to a certain extent. I would actually put up a special tutorial just on how to do the welds for atom probe samples. If you can influence your geometry and align your lift out piece or your weld perfectly to the gas injection system and produce a good geometry, that makes a huge difference in sample survival rates. And because it's so important, I will go into detail into that in an entire separate tutorial. So if you look from the side, which unfortunately in the machine, in the FIB, you can't really do, it would look something like this. So the whole assembly, you've got the bar cut from the side, and you've got your support structure cut from the other side, and then hopefully perfectly aligned, joined together when you move the support structure to the lift out piece. And the arrow here shows you which side the gas injection system and sort of which angle the gas injection system would come in at the side. It comes in a bit more from the top on the FIB machines, if it's the primary GIS that you're using, and also at the size machines or any machine that uses also physics equipment, which is size and test can. If you're using the mono GIS, if you use the multi GIS, which is the 5-channel GIS on the size or machines with also physics equipment, it will come into the shallow angle. So the thing with the gas injection systems is that they're actually designed to deposit onto a flat surface. And we, in Atom Probe, we are one of the few people that have actually entirely different geometries. So we're a little bit forced to work with that. But always bear in mind that you would like to have no shadowing in terms of where the gas goes, and generally have the gas going at the same angle on every facet that you're trying to deposit on, as otherwise you're going to get obviously uneven depositions. There's unfortunately the optimum conditions we can't usually reach, especially while you're doing a lift out, because you have your sample still on the micromanipulator. But again, that's topic for another tutorial. If you have platinum, which is what a lot of people have on their machine, so again, it's trimethyl platinum, blah blah whatever, a lot of carbon in there, then the geometry constraints are not as bad because it sticks very well to everything, and it's not that often gas limited. It still can be, and it is pretty often, but not as often as, for example, tungsten hexacarbonyl, which is another pretty popular one. On my webpage, you'll also find a little bit of a guide to the different deposition conditions and different deposition materials. But of course, the cleaner your deposition material is, the stronger your deposit will be. So platinum, easy to deposit, but also the weakest welds. Tungsten hexacarbonyl, a lot more difficult to deposit. you need to be very careful about the geometry. But if you get the position right, the welds will be very, very strong and will have very good survival rates. In the microscope, the whole thing will look like here then. So you're seeing the support structure, which is a molybdenum grid in this case, which is being cut at an angle, and the lift-out bar. And so the green box on there, on the FI, this is an FI instrument obviously, the green box is the position for the gas injection system, and the yellow box is the cut for that removes your little lift-out piece from the rest of the bar. So this is once again a very critical step, because you have your lift-out bar, which is attached to a chamber, in contact with your support structure, which is in touch with the stage. So if you can't lock the stage, if you accidentally click somewhere and things start moving, things will also start breaking. So the most basic thing about the deposition conditions is, where does my gas injection system come from? In this case, this is our FEI Quanta. It comes from the right side, which means that the green box, which is the deposition, we will set the scanning conditions from left to right. So from away from the gas injection system towards the gas injection system. And also, if there's some gas limitations, we will put some refresh on the pattern. So in this case, the refresh is 2 milliseconds. So between every single scan, it will take 2 milliseconds break and let the gas refresh. The weld itself, even though here it says 50 picoamps, the weld itself is actually done at 10 picoamps, because that gives very fine welds. Again, later tutorial, I'll show you TM images of what sort of difference that will actually make. Then the weld in this case will then take about 5 to 6 minutes, which is a little bit longer than if you use not as good deposition conditions, but because it gives you much better sample survival rates, it is actually worth it. Another thing about the patterns, all of the patterns that you see here, I'll also throw up on the web as well. So they are FEI PDF files. You can use them on your instruments, and we'll have all the scan strategies, refresh and everything on there. You might need to adjust all those things to fit your specific geometry though. One thing then, when you finish deposit, I tend to just let the machine automatically switch over to the cutting pattern, which is the yellow one here, and cut off the lift-out piece from the bar. The one thing that you have to make sure though is that there is enough time for the machine to pump away all the gas, all the precursor gas before it starts cutting, because otherwise it will not actually start cutting. It will start sort of half cutting, half depositing, which can actually give you some trouble then when you're actually trying to remove the lift-out piece. So depending on how well your pumping system is working at the moment, this can take anywhere between half a minute and 2 to 3 minutes. Once you're finished with the cutting step, it should look something like this here then. So you can see again there is some voltage contrast between the lift-out bar and the lift-out piece attached to the support structure, which tells us that the cut's gone all the way through and there's no contact anymore, and it's safe to move your stage now. Always try to remember what sort of stage command will make your stage move into the right direction, because you get it wrong, you'll break your assembly. Once again, this is one of the critical points where if you move things the wrong way, things will break. Simple, just try to remember which way you're moving things. In this case, the weld is actually a weld that I would use directly, so there's no welding involved anymore in that I do in an optimized geometry where I've got better gas flow or better precursors or whatever. I know roughly that these welds in these settings that I do here, which is 10 picoamps and this sort of GIS geometry, will fracture somewhere between 7 and 8.5 kV in the atom probe, which does the job decently well. There is a certain failure rate attached to it, but it saves you a reasonable amount of time in the FIB, and therefore I still use it for quite a few lift-up pieces. Well, from there on, it's step and repeat, really. So you do the steps with the attaching and with the approaching, attaching, welding, cutting off, for however many samples you want to make. Usually on a grid with 9 pins, which is done at 100 mesh, I would make 5 samples. I would skip every other pin simply because if they're too close together, one tip flashing in the atom probe will damage the next tip. It just happens. I think if they're closer than 250 microns, that's what happens. Once you're finished with that, you just retract the gas injection system, retract the micromanipulator, and you drop the stage and you're good to go for the next bit, which is the shaping of the atom probe sample and the targeting of your feature of interest, but that will be the topic of a different tutorial. Well, I hope you've made it that far on your own system. So if you've got any comments or any suggestions, let me know. Put a comment on the video, because after all, making atom probe samples, sample preparation in general, is it whatever floats your boat topic. So different people will have different approaches, and if it works, it works. I'm not saying this is the absolutely best way that things can be done. Maybe there's some better ways somewhere and some improvements. We are still continuously improving our techniques. So if you think you've got something that works better, please let me know. I'm always really, really curious about what other people are doing in that field. Because after all, I think if we all combine our little tricks and our approaches, we can all do quite a lot better and improve our survival rates. And I don't think any one of us is gonna run out of work anytime soon anyway. So all of the supplementary material to that video, like the basic guide, for example, and things like that, I'll throw up onto my webpage. So you can download it from there, and also make an effort and get all the patterning files that I'm using on the FEI systems and throw them up as well, so you can use them. I think they're pretty much compatible between all the different FEI systems. I have to have a look into the size system, so I use on the size systems, on our size system at least, I'm using the FIB patterning engine, which is a very good 60-bit patterning engine, and I like the interface and the abilities that it has very much. I just haven't saved as many or developed the patterns that I'm using on there as much, whereas the patterns that I'm using on FEI Quanta, I've used on a variety of different FEI machines. Settings work very well. Of course, they're only honed on the standard settings. So this means you have a platinum gas injection source, and that's the basics you work with. But that's probably what most of you people out there will have anyway. And one last thing that I want to say about everything that was in this tutorial. Everything that was in this tutorial was done at an ion beam acceleration voltage of 30 kilovolts, 30 keV. So this is the most standard setting in most of the focused ion beam systems. I know that Hitachi uses 40 keV for some strange reason, but most of the systems will run on 30 keV. Up to a certain point, it's actually okay. So as long as your lift-up piece is larger than a micron in any direction, that's okay. Once we're getting smaller, we actually need to work at a lower acceleration voltage. So as soon as your lift-up piece is smaller than, say, a micron, you will need to use 10 kV or below. Or on the FEI systems and the Helios, this means 8 kV. They don't have a 10 kV setting. Because this means that you'll get less ion damage on your samples. Less ion damage means within the region of interest, you should not find any gallium at all. None at all. If you do, you can't do any fine scale analysis because the damage is prohibitive of any clustering analysis, anything along those lines. And additionally, it will actually increase the survival rate of your samples significantly. So if you lower the ion damage in your samples will have a much, much better survival rate. But again, that's the topic of a different tutorial. Most of the things that I've said here, you'll be able to find in a paper that I've published last year. In that paper, I mainly tried to focus on the things that people have been asking me quite a lot when they were contacting me about how to make their samples. So it's more about what influence do certain ion beam settings have on the geometry of your samples. How do the welds work? What's the effect of ion damage? And also, what's in there is the geometry of how we do lift out on grain boundaries. If you want to measure them sort of perpendicular to the measurement direction of the atom probe. And also the design of the holders is published. The design of the holders that I've been using in this tutorial is published in there. If you want to reproduce them yourself, you can find them in there. So please, if you've got any suggestions, add comments, or tell me what your approach is. I'm always curious. And I'll see you in the next tutorial.